Professor R. Asokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series meant for BSc Honours Physics students. We are going through a set of lectures on optics, and especially we are concentrating on diffraction, and in the section on diffraction we are going through plane transmission grating and the zone plate, the diffraction grating. So the contents of this lecture are transmission grating, determination of wavelength of light, zone plate, comparison of the zone plate with a convex lens. As I told you in the last lecture, a grating is nothing but a glass plate in which you got number of rulings and spacings. What do you mean with spacing? It is a space available for the light to be transmitted. That is the reason why it is called transmission grating. Light can pass through the opening. This opening is similar to what we saw in the Huygens experiment, wherein you got only 2 slits, but here you will be having how many slits? As I told you in the last lecture, there will be 15,000 LPI, 15,000 lines per inch, or 15,000 spacings or openings will be there. So a diffraction grating is an extremely useful device, and it consists of a very large number of narrow slits, not 2 slits, but 15,000 slits placed side by side. The slits are separated by opaque spaces. When a wave front is incident on a grating surface, light is transmitted through the slits and obstructed by the opaque portions. Such a grating is called a transmission grating. You got a transmission grating. You see here the openings through which light is coming. The light is being bent. It is bending. So the light beam that is being bent, it is made to come to a focus by means of a convex lens, a condensing lens, which is used to bring the light into a focal point. The P is the point where the light comes to your focus. So if you have got a white light here, a grating will act like a prism. What do you observe in the case of prism? A prism placed in the path of the light beam, all of you know, as was observed by Sir Isaac Newton, or perhaps it is climbed, it is Hooke who saw the phenomenon of dispersion, the splitting of white light into different colors in the order of Vibgyor. Similar to the case of prism, which shows white light consists of different colors in the order of Vibgyor, violet, red. A diffraction grating also acts like a prism. If you have got a white light here on the left hand side, the light passing through a grating will give rise to all the colors in order of violet, blue, green, yellow, red, orange. Okay, finally red, right? The order of Vibgyor. So the angle theta is important. The angle of diffraction will be different for different colors, and I will come across an expression which connects the angle theta and lambda. So theta will differ for various lambdas. I told you that white light consists of violet, blue, green, yellow, red and so on. So the different colors will have different angles of diffraction. Theta will vary for different lambdas. So now pass on to the secondary waves from the positions of the slits interfere with one another, similar to the interference of waves in Young's double slit experiment. Gratings are prepared by ruling equidistant parallel lines on a glass surface. Such surfaces act like transmission grating. So Xy is the grating surface. That is what I showed here. Xy, the grating surface, and Mn is the screen, both perpendicular to the plane of the image. That means you have got a grating here, you have a source here, you have got a grating here, like a prism kept in the path of the light beam, and you have the telescope through which you can see the different lines or colors. Okay, the slits are all parallel to one another and perpendicular to the plane of the image. AB is a slit and BC is an opaque portion. The width of each slit is A. The width of each slit is A, and the opaque distance, the thickness of the opaque distance will be B. So A plus B is called a grating element. It's called a grating element. Let a plane wave front be incident on the grating surface. These secondary waves traveling in the same direction as that of the incident light will come to a focus at the point P, as I told you earlier. The screen is placed at a focal plane of the collecting lens or the converging lens. The point P where all the secondary waves reinforce one another corresponds to the position of the central bright maximum. So these secondary waves coming through the slit, they come to a focus at a point P1, which will depend upon the path difference between the secondary waves originating from the corresponding points A and C of the two neighboring slits. AB, as I told you, is A, small a, that is the width of the opening. BC will be the width of the ruling. You have got a ruling spacing, the opaque distance through which light is not being passed, and this is the opening, the width of the opening through which light is passed. As I told you, A plus B is called a grating element. The path difference between the source, between the light beam, the secondary waves starting from A and C should be measured. The points A and C are the important points. You look at the diagram again. You have got A and C here. A is here and C is here. The path difference, this is the path difference. You see the light beam coming here. This light ray now, supposing you call this as the light ray is C, it undergoes a bending, whereas this you have got undergoes a bending, it goes like this. But what is the distance travel by from here to here, from here to here? This light ray travels through an extra distance. You always know that the path differences are constructed. You know what is the path difference? The extra path traveled by one of the light ray or one of the light beams compared to the other beam. So you got two parallel rays of light. You got one line here, another line here, theta is here, okay, and this is the extra path, right? This is the extra path. This is the path difference, okay? This is the path difference. Under what condition you will be getting brightness at a point P? You all gone through the superposition of waves. When waves are meeting each other, we talked about constructive interference, destructive interference and so on. So the path difference should be what? Should be integral multiple of lambda for getting constructive interference. For getting destructive interference, it is odd multiple of lambda by 2. You all know by now the path difference should be set equal to n lambda for getting constructive interference. The point P, you want to have a green line or some blue line. You got a bright line. The point P will be bright if the path difference that you got here, this is the path difference, right? Or between this point, this ray and this ray, the path difference is so much, right? Okay. If you are considering this light ray and this light ray, again the angle is the same theta, the path difference is so much. This is the extra path. travel by this light ray compared to this light ray. This is the path difference. But for these two rays, path difference is so much. Between these three, this one and this one, it will be so much. So this is the path difference, right? This path difference should be integral multiple of lambda, then only P will be bright. If it is 2n plus 1 into lambda by 2, that is the condition for darkness. And so I am going to do these things now. I am going to show that your the path difference between the 2 points A and C will be equal to AC sin theta. You have got AC sin theta, that is the path difference. This path difference AC will be AB plus BC, that is the grating element, that will be equal to AC sin theta. AC sin theta will be what? A plus B into sin theta. This A plus B is known as the grating element. What is the grating element? Grating element is, as I got line here, AB is called a grating constant or grating element. The grating element means the width of a spacing and the width of a ruling. The distance between the ruling and the spacing. A distance covered by one ruling and one spacing, that is called a grating constant, right? For a grating which is usually used in the laboratory, as I told you some time back, there will be 15,000 lines per inch. It would have given, you see the grating, there will be 15,000 LPI, lines per inch. Therefore, for a grating which is having 15,000 openings, then your A plus B, that is a 2.54, that is your inch is 2.54 centimeter, that divided by 15,000 will give you obviously A plus B, that is the width of the ruling plus width of the spacing. That is your grating constant. Those of you who do the experiment in the laboratory using the grating, what is the experiment you are doing? What is the aim of the experiment? The aim of the experiment is to determine the lambda of the various lines. As I told you, I showed you the experiment setup. You got a grating here, you got a source here, you got a grating here, you got your optical instrument here. To see the lines, you got a spectrometer. You take a spectrometer. You have done, all of you should have done the grating using the spectrometer. There is a prism table or the grating table, and you got a source of light here, grating table is here. You got a telescope. You can move the telescope, see all the lines in the order of Vibgyor, violet to green, red, and so on. The wavelengths of the various lines can be determined using the diffraction grating or the transmission grating. The formula to be used is sin theta is equal to capital N into small n into lambda. What is small n? Small n is the order number. What is capital N? 1 by A plus B. You take this A plus B to the right hand side, it becomes 1 by A plus B. In 1 unit length, how many A plus B's are there? That is the number of rulings made or number of grating elements that you have got in the grating. That is 15,000. That will come into the right hand side. Sin theta will be capital N into small n into lambda. That, you know, the formula is a very well known expression. So the formula that you are using is sin theta will be n into lambda, where capital N refers to the number of rulings that you have got here, 15,000 the grating elements. Okay, small n is the order number. You know, when you are using a spectrometer and you have got a grating there, you get a first order spectrum. N is the order number, n lambda, right? So the first order, second order, possibly third order also. Okay, so n is the order number, lambda is the wavelength used. So by measuring theta, right, measuring theta for various lines, you see the spectrometer, you have them all the lines, violet, violet 1, violet 2, blue, bluish green, green, yellow 1, yellow 2, and so on, red. So you make the crosswire to coincide with each and every line, measure theta. What is theta? Theta is the angular difference between when light is coming straight, right, that is the 0 position. Then you move the telescope through some angle so that the violet line is made to coincide with the crossfire. That angle is theta. Then violet 2 to coincide with the crossfire, that is theta 2. Then green, that is your theta g. Then yellow, theta y. Then red, theta r. So you make the crosswire to coincide with various lines and measure. You know, the theta can be measured, as I told you. You have the direct line, the white light is coming directly, you make the angle, measure the angle, and then for various colors measure the angle. And by measuring thetas and substituting the expression, the wavelength of the various lines can be determined. Let us have a break at this point. Welcome back at the break. The grating, as I told you, consists of 15,000 grating elements. A grating element or a grating constant is A plus B, the width of the ruling here, the width of the spacing is the slit. Then A plus B, the grating constant. So, using this expression that you got here, which connects theta and lambda. What is theta? Theta is the angle of diffraction suffered by the violet line or the violet ray or the green ray or the red ray, right? You get all the colors. As I told you, the grating is similar to the case of prism. When white light is passing through a grating kept on a spectrometer, you can see all the colors in the order of Vibgyor. And so now let us keep grating on the prism table. You got a spectrometer. For white light, using a spectrometer and placing the grating in the prism table, the angles of diffraction of the different lines can be measured, and hence the wavelengths can be determined using the formula which I showed you just now. Therefore, we have to accurately measure the angles of diffraction. I told you how to measure the angles of diffraction. The spectrometer, you assume that the grating here kept on the prism table or the grating table. What is this? You have got a telescope here, you got a source here, right? You got a source, light is coming from the source, passes through the grating. The white light gets split up into different colors. First comes, you have the violet here, blue here, bluish green here, yellow and red. P is a point where you may probably see the red line. So, you have, as I told you, blue here, green here, yellow here, red here. Then you move the telescope still further, you again get the repetition of the same lines. Again you have got violet, blue, green, yellow, red and so on. That is the second order. So, this is the first order, this is second order. So, the order number is pollen. In the expression that I had, the order number is pollen. Having determined, you have to measure what is this, the thing to be done. You place the telescope here. When you got white light, the white light is coming, it's called the direct ray. The direct ray can be made to coincide with the crossfire. When you place the telescope here, the telescope is kept here, you see them direct white light. Take the reading in the two verniers, take the readings, then move the telescope to coincide with the blue line, then the green line and the red line, all the various colors. So, when you move it, this is the angle theta, the angle through which is moved. You know, this is the straight line, the ray is coming here, and the angle through which you have to move the telescope to see a particular line. P may refer to the green line or the red line or whatever be the line. So, the angle through which the telescope should be moved from this point to this point, that gives you the angle of diffraction. Now, substituting the angle of diffraction in the expression that I showed just now. So, substitute the theta for different colors, right? Different colors, violet, blue, green and so on. Use the expression and determine lambda. You tabulate all the wavelengths. So, what is the use of the transmission grating? Transmission grating acts like a prism. You get all the colors for white light. The wavelengths of the various colors can be determined using the transmission grating. The formula to be used in this case is given here. Okay. Let me now pass on to the next part of the zone plate. Zone plate I am going to finally show. I will come to a comparison also. Zone plate acts like a convex lens. What is then the zone plate? How to make the zone plate forms the first part, and the way in which the zone plate is made and how the light will be passing through the zone plate, These things will make you to recall what you have seen in the earlier lecture when we try to explain the rectilinear propagation of light. It's called zone plate because of the fact that I will be again talking about the half period zones. Remember the half period zones that we made use of to explain the formation of shadows. The same way we are going to now prepare the zone plate. A zone plate is a specially constructed screen such that light is abstracted from every alternate zone. Light will be abstracted from the first zone. If it allows light, the second zone will cut the light. The third will allow, fourth one will cut, fifth one will allow. So light will be coming from the first zone, third zone, fifth zone, or the contrary. You can also have, you can make the light to be cut when it comes to the first zone, then the light will be coming from the second. Then in such a case, the zones 2, 4, 6 will be transmitting light. The zones 1, 3, 5, they abstract. You can have either way. Okay, it can be designed so as to cut off light due to even numbered zones, or that due to odd numbered zones also. You can have light to be transmitted only through the zones 1, 3, 5, or only through 2, 4, 6. So alternate zones alone, not successive, only alternate zones only will allow light to be transmitted. How do you make this zone plate? Before that, the correctness of Fresnel's method in dividing a wavefront into half period zones. How Fresnel talked about half period zones, to what extent is correct. So this comes as a verification of or offering explanation for what Fresnel did to explain the formation of shadows, the justification of what Fresnel did in making a plane wavefront and to treat the plane wavefront to be made up of half period zones. That is coming from whatever that the result that you get. It supports the ideas that are propounded or proposed by Fresnel. That is, the correctness of Fresnel's method is supported by what you call a zone plate. Now we will see how the zone plate is made. A zone plate is constructed by having concentric circles on a sheet of paper such that the radii are proportional to the square roots of the natural numbers. Now it is shown in the figure. We saw in the in the theory of the rectilinear propagation of light, the radii of the zones are proportional to or directly proportional to the square root of natural numbers. Same way you construct zones. How do you construct? The zones are constructed. You take a paper and make this kind of you make it dark. You put ink and make it dark. The first half period zone is darkened. Similar to the darkening of the first half period zone, you should darken 1, 3, 5, 7 and so on. You have to darken the zones. Then you take the negative of the thing. Negative of the photograph will be given as A. This is the positive. The negative will be, so if one is dark in the negative, one will be bright. So I am showing only the first zone for clarity. In principle, the first zone should be darkened. Third one is the second. The second will, in principle, second will allow light. It is your final, zone plate. This is dark, it will not allow. This one will allow. Then this should be dark again. This will be bright. This will be as it is, the white paper. Again, this should be made dark. So one is made dark. Third zone will be dark. Fifth zone will be dark. So the first zone will not allow light. You take the negative of that. That is the one that you are going to consider now. The negative of it will be the first zone, which is darkened by having some ink or something on a sheet of paper. That is your zone plate. The first one is darkened. The negative of it will be plain white paper. That will allow light. So this is dark. The negative of it will allow light. So light will be allowed by the first zone, third zone, fifth zone and so on. So zone plate as shown here, you can construct the zone plate in such a way that light that is passing through a piece of paper, a transparent paper, light source is here, you have a transparent paper, through which light will be passing. If light passes through the first 3 and 5, or the other way around, as I told you, you can make 1 to be dark, 3 to be dark, 5 to be dark, or you can make 1 to be plain, bright, 3 to be bright, 5 to be bright. In either way, both of them are called zone plates. The negative of the photograph that you have here will become the zone plate. The drawing appears as shown in figure B, wherein light will be allowed through the first zone. Second should be dark. Third one will be again like this. So light will be passing through alternate zones. In the developed negative, the odd zones are transparent. 1, 3, 5 are transparent to incident light, and the even zones will cut off the light because they are shaded as dark. If such a plate is held perpendicular to incident beam of light and a screen is moved on the other side to get the image, it will be observed that maximum brightness is possible at some position of the screen, say B centimeter from the zone plate Xxxiii in the upper half of the incident plane wavefront. What I am trying to tell you can be seen in the diagram here. Xxxiii, where is Xxxiii here? You got X here, O here. Xxxiii is nothing but, you see, light is, this should bring back to your mind what we saw in the Fresnel's theory of rectilinear propagation of light, wherein we had a point P again separated by a distance B from O, that O is a point on the plane wavefront. We drew circles, right, or spheres with P as the center. We drew spheres with B plus lambda by 2 as the radius, B plus 2 lambda by 2, B plus 3 lambda by 2. These spheres intersect the paper or intersect the spherical wavefront or a plane wavefront. These are considered as a plane wavefront, right? You have got a source here, it emitting spherical wavefronts. As I showed you in the earlier lecture, a part of the spherical wavefront will be a plane wavefront. In the plane wavefront, you will be having the first zone here. How do you consider the first zone? B plus lambda by 2 as the radius. You draw a sphere that will cut and produce the first half period zone. So this is the first half period zone, the second half period zone, and so on. So you have the different half period zones. The same way zone plate is constructed, having P as the point at which light intensity is to be considered. The distance of the point P from the wavefront is B. Then draw circles with radii having B lambda square root of natural numbers. Then you get different half period zones. Let me now summarize what I said so far. A diffraction grating consists of rulings and spacings. Diffraction can be used to determine the wavelength of spectral lines. In the case of zone plate, as the distance of the source is large, the incident wavefront can be taken as a plane wavefront with respect to the zone plate. The intensity at any point P is obtained from the light passing through all the zones as done in the earlier studies. The questions are, what kind of wavefront is incident on a diffraction grating? What is grating constant? What is the formula which helps one to determine the wavelength of a given source of light? What is zone plate? How is it constructed? With this we come to the end of this lecture, and in the lectures to come we will see more about the zone plate and the connection between zone plate and a convex lens and other things as found in the syllabus. Thank you.